Let's make sure that we understand some basics. We mentioned yesterday that any software lives on your hard drive as a file. When you run this file, let's say this is an exe, when you run this file, it moves to the memory in a form of process. Now, inside this process, we need to execute a few lines of code. We call this lines of code threads. And the software may be a process with one thread or more than one thread, or even more than one process and execute things in what we think it's parallel. However, what I want to describe right now is that we literally do not have real parallel processing. Why is that? We do have to a limited amount. This is a bad example to show you this machine because this is a very powerful machine. But if we want to see what's inside this machine, let's look at these numbers here. We see that inside this machine, I have 674 processes, and inside these processes, there are threads, and we have 3,250 threads in average running simultaneously on this machine right now. That includes tablet, my keyboard, my mouse, my two screens, my Teams, streaming up, down, up, the network up and down, everything, all of these processes. Here we see a list of all 674 processes running. But if I want to see more stats about this machine, I don't know, where can I show you these stats? Maybe about this Mac. Yeah. So as you can see for this machine, I have here 8 cores. I don't know if you can see that as well. So this machine has a CPU that has 8 cores. 1, 2, 3, 4, 5, 6, 7, 8. And this is considered like a top-end machine with this number of cores, because probably the operating system is able to see these 8 cores at 16 cores. We will see that next. However, I'm running 3,250 threads on 8 cores. So physically, I have 8 things happening in parallel. That's a real parallel. I have 8 things running at the same time. And if 8 things are running at the same time, that means I have 3,242 waiting. But I'm managing to run all of this at the same time, but not in parallel. We process all of these in concurrent way, concurrent processing. So what is concurrency? Concurrency is the art of alternating between all of these threads based on priority to give you the impression that all of them are running at the same time. So imagine you have 2 threads need to run in a single core. So we process the first bit of the first thread, and then we pause We process a little bit of the second thread, and then we pause. Then we process this more part of the first thread, and then we pause, and then we process more of the second one, and then we pause. So you would assume that this number is divided by 8. Okay, the number that we get is the number of threads that are running on a single core in my CPU. So physically, we don't get real parallelism, only to a limited amount. How many things are really running in parallel? But when we see, like, I have here a service, yeah, and this service has 10 threads, 13 now. 13 threads are need to run at the same time. They are not running in parallel. They are running in concurrent way. That's the job of the operating system. This is something we don't interfere with. The operating system delegate in what we call operating system hyper-threading. It's a feature of the operating system level. It's called hyper-threading that process all these threads on limited core in concurrent way. That's how things get done. Any questions about this process? Now, we have a concept called I/O, which is a shortcut for input output. What is I/O? What's input output? To describe I/O, I would say I/O is any operation that is foreign to CPU. So we have a CPU with a certain amount of cores. Any operation that requires read and write to any unit outside the CPU is considered I/O. So we can list reading from L1, L2, L3 cache. The cache is outside the CPU core. So this is I/O. Reading from RAM is I/O. Reading from the hard drive is I/O. Reading from the network is I/O. So all of these operations are defined as input-output. They are operations that requires read and write from certain place outside the CPU. Any questions?
Professor, I have the question on the previous
Yes.
part, not the IO part. I have the
Yes.
questions on trading.
Mhm.
So
Yeah.
so so as a process can have multiple thread
Mhm.
and process, I mean, and the thread of the same process usually share a lot of resources through the process control board.
Mhm.
Uh,
What's the question?
so my question is that is there any possibility that a multiple thread of a single process can run simultaneously in the different core?
It's unlikely that's going to be the case. Remember, a regular machine probably will have like 4 cores, seen as 8 by the operating system, with a number of 3,500 number of threads running. It's unlikely that these 2 threads will be in 2 different cores. This is very, very unlikely. That's why I would always describe processing that parallelism is rarely really exists. What really exists is
Concurrent.
concurrency. But we will see at the end of tomorrow's lecture that we could guarantee that we run our applications on separate cores And within each core, you run one part of the application. That's something that we could determine at some point. But to have one process that has multiple threads, to guarantee that these threads are divided on multiple cores, that's something I never experienced with or never saw.
So I have the follow-up question on that.
Mhm.
So if the all thread goes to the same core of I mean the respective process,
Mhm.
so then how they can communicate through the port? As far as my knowledge, that thread can communicate or share their resource through the port. So
Yes. Yeah. Another idea that we will discuss in details tomorrow when we build
okay.
clustering. Yeah, we will see that when you build a cluster, there will be some sort of a router, and all instances of the app, they share the same TCP connection, so they share the same whatever port that you choose for your application. We will discuss this tomorrow.
Yeah, yeah. Thank you, Professor.
Any other
All right.
questions?
And I'm good.
So we discussed processes and threads. We discussed I/O. With I/O comes a concept called I/O latency. What is latency? It's the time that we receive a response. You have x equal y plus z. To read the value of y, there is latency. To read the value of z, there is latency. Y lives in memory, z lives in memory. So you need to read y. I need y. The time between you ask for y and you receive the value of y, we call it latency. And everything, any operation in the hardware physically has latency. I'm going to show you here a slide called I/O latency. And in this column, we really see the real latency for some operations. So to read from L1, L2, L3 cache, we need a range of these times. All of that assuming that one CPU cycle, which is a regular number, the one CPU cycle is 0.3 nanoseconds. To read from the RAM, we need 120 nanoseconds, which is what you see the RAM is clicked, but the frequency of this RAM. To read from solid state disk, to read from a rotational disk, now we're seeing milliseconds. You see that? To read any data over network through the internet, probably you can measure that easily in your application. The time you send a request to your API and the time you receive a response, which is around, I would say 150 milliseconds is considered pretty good time for a request and response over the internet. This is still under 1 second, which is 1000 milliseconds. So it's all of these operations are considered really fast. So if your code was synchronous and one line of your code is to read something from DB, that would be 150 milliseconds because your database in different machine, 100%. Then we have like another 10 milliseconds to read from the rotational plus processing. Let's say reading from DB will require 200 milliseconds total. You get the results and then you continue processing. That's considered good, normal in any application. But now if we compare the real time inside the CPU to human time, so all I'm doing is calculations. I'm assuming that the 0.3 nanoseconds is 1 second. Why? Because as humans, we perceive time by the second. We cannot perceive nanoseconds. So I'm just converting these numbers and I see that, hey, for the time I can read something from the database, that would require 1 year plus 19 years. That is like a total of 20 years. I'm stuck at one line waiting for the database to give me results. So if I am allocating a thread just to run the scripts, just for the scripts, this thread will be stuck for 20 years waiting for the DB to bring me results before I can process the next line or any other scripts. So I see that we do have a problem when we design software. However, if I design this code to run asynchronously, I send the request. I need this data. I don't care if it takes 20 years or 40 years. This thread can be allocated different job. It can allocate to serve different requests, different client, send a response that's ready to be sent, right? So we can take advantage of all this latency that's happening within the CPU. And hence, there was the design of Node platform. So when we see the Node platform, it does have a single threaded event loop. But somebody might question how a single thread is more efficient than multi-threads. The answer is, if I allocate one thread for every single request, I have multiple problems here. The first one is synchronous code is going to have a lot of latency and literally a waste of processing inside my machine. Another problem that we have is allocating more threads for every request that we receive. We face a problem of limited thread pool because threads lives in memory. And in every operating system, we have certain amount of memory that can single process consume. We can spin more and more and more. So we have a thread pool. Let's say we can spin 50 threads or 500 threads. That's it. It means I can run 500 requests at a time, and then I'm done. That's very limiting. So for that reason, to scale a web application, we don't like to spin more threads. Instead, Node is designed differently with a single threaded event loop that takes care of more requests over time that are covering all the I/O latency that's happening within the hardware. We mentioned a lot. Let me give you a real-time, real-life example. We're all hungry. We didn't have breakfast, and we are going to McDonald's to order food. This is McDonald's. We are 25 people heading to McDonald's to place orders. McDonald's run similar to Node.js. They are smart. They don't run with a multi-threaded system. They have a single cashier. which is one event loop. Imagine McDonald's works spinning more cashiers as more clients are coming. That's not how McDonald's works. So when 25 requests all arrives to McDonald's, a single cashier is enough to take all these orders. Let me give you the example of, let's assume that McDonald's is a multi-threaded system. In that case, McDonald's will anticipate that, oh, I have client, allocate cashier, another client entered, allocate more cashier. Every single time you receive request, you allocate a thread. At some point, McDonald's has thread pool. It cannot spin more than, let's say, 20. And now 5, so 20 here, and now 5 are waiting. Their turn, they cannot place order. This client waiting now, place an order, and now waiting for the burger to finish, receive a response to open up a space for an upcoming client. So multi-threaded system has the limitation of thread pool, not scalable. And that's not how things work in real life. Instead, I'm going to tell you how McDonald's works. McDonald's has a single event loop. All 25, nobody's waiting. They can come and place orders right away. Hey, I want burger. It is a callback function. When your order is ready, I'm going to call you. They give you immediately a pager, an order number, that when your order is ready, we will call you back. So all 25 requests, probably 50 people are coming. No one is waiting. Every single one comes, place an order and receive callback function. Place an order, receive callback function. Nobody's waiting. So all 50 or 100 or 500 clients can enter McDonald's and all of them satisfied with a single event loop because they can immediately place an order and receive a callback function. So there is no waiting when they place the order. And that's more satisfactory than placing multiple cashiers and each one is blocking the upcoming clients. So things in real life work in asynchronous, non-blocking way when we place orders. Now, that's not all the story yet. So we're happy that we have single event loop that takes care of all the upcoming requests. What about the kitchen? McDonald's also has a kitchen in the background that we don't perceive. And this kitchen is I/O, everything outside your application. I/O is where the burgers are prepared. So imagine in the kitchen, we have one chef that needs to take care of 500 burgers. Imagine this kitchen I/O is preparing one burger at a time and then sending the burger to the client. That would be non-efficient. And also the kitchen cannot spin more chefs. Oh, I have 500. Hey, bring 500 chefs over here to prepare one burger for each client. Also, that's not how the kitchen work. So in order to have an efficient, scalable kitchen, a single chef is enough as well. Single threaded event loop in the kitchen. How it works? A single chef can put all the patties on the grill, flip them all one after the other, put them in buns one after the other, prepare all of them in kind of concurrent way, and start sending them as they are ready. So also one chef is enough to scale and serve more burgers as they arrive to the McDonald's restaurant. So if we do business at a corporate and big scale restaurant like McDonald's in this way, why don't we do the same when we design software? And that's exactly how Node perceived the I/O latency problem and designed Node in the following shape.
Professor, I have comments.
Yes.
Node.js, what I've noticed that here, it's actually efficient if there is a lot of I/O works. So
Mhm.
if there is like a lot of CPU works, like calculating a lot of mathematical operation, that time
Mhm.
Node.js is not efficient.
Correct.
And furthermore, nowadays the previous even I'm just confused. Why are you comparing the thread with asynchronous processing? There are two different things.
Yes, correct.
So
They are completely two different things.
yeah,
And this
yeah.
is the next problem that I'm going to discuss.
Okay. All
Yeah,
right.
yeah, be
So
patient.
since
Yeah.
not only the Node.js on right now, like .NET and other stuffs usually support asynchronous, and
Correct.
they usually follow the state machine, and
Mhm.
since they are also support the multi-threading environment, so
Mhm.
these things, from my understanding, is very efficient compared to Node.js, since if any thread is nowadays thread is not waiting to task to be completed. In the meantime,
Mhm.
they maintain the state machine, and they return to the thread pool and available to accept another request.
The difference is in other programming languages, you need to code things this way to make them asynchronous. While in Node, all Node API is by default works this way. So you don't need to code differently to make them asynchronous. They are designed already in asynchronous way and non-blocking IO. So that's the only difference. But yes, many languages as well, they started supporting uh, running things asynchronously.
Thank you,
Okay.
Professor.
Uh, so what I explained earlier is that if we're processing things, if we were spinning one thread for every new request coming, we end up with a problem that client number 5 and 6 and 7, all of them are waiting their turn because I reach a thread pool limit within this process, and that's not scalable. And probably the single request will require more than one. For example, you read something from the database, you process it, you read something else. So other requests within the same client, if they were not immediately sent, I need this and I need this, then they will be waiting. And that's another kind of blocking problem because uh, you're wasting processing time inside the machine. And the other system, the problem that we see in traditional web servers, this is traditional web server like Tomcat or Apache Tomcat or IIS or WebLogic. That's a default. And all of these web servers, they have an IO API that's really blocking. You can't process things in non-blocking way. So to solve this problem, Node, when it was designed, now I can say 13 years ago, it was designed in a way that Node has one single event loop that process all requests, schedule all requests, to acknowledge all of these requests at once. So nothing is being waiting, and that's more scalable. And Node, while it has a single event loop thread, has multi-thread system for the I/O, and the I/O is designed in a non-blocking way. So it's really a misconception when somebody try to describe Node by saying, oh, Node is just have a single thread. No. Single thread of what? Yes, Node does have single thread event loop, which is like the maestro, orchestrating all of these events and stuff. However, Node server has multi-thread system in the I/O, and the I/O also is designed in a non-blocking way. So this is very important difference when we describe Node. So since my application, that's coming back to Abdullah's question, since my application has a single thread event pool, and you would assume that this event pool is dealing with some sort of queue to process some functions in V8. At some point, we also have a single instance of V8 that's running all the code synchronously. Now, if you're running blocking code in V8, then your event loop is going to be blocked. And yes, you are acknowledging all the requests. None of this request is being processed because this is where they are running and process. This is just scheduler. So we need to make sure that we write non-blocking code in order to keep everything running smoothly. And this is the concept that I want everybody to understand deeply today. Tomorrow we will see that, hey, what if I do have to block V8? How can I solve that? And we will learn how we solve it. Tomorrow I want you to identify and understand the problem. So if we want to look at how really Node server is designed, we will see something similar to what we learned yesterday in the browser. Every single time you run Node, you create a process in memory. And this process, this is Node.exe. And this process has some threads inside. One of the threads is V8. And inside V8, inside the Node process, V8 is synchronous, you remember? Where is the asynchronous part that we run set timeout and stuff and other asynchronous parts? We have something in Node called libuv. This libuv is where the asynchronous operations happen. This is where the set timeout is sent to. You can imagine that inside this asynchronous part, we have queue that you can push functions inside. You can imagine that there is an event loop taking functions from the queue and pushing them to the stack whenever the stack is empty. And this event loop is one thread. So Node server is one thread event loop. It has one thread V8 plus has multi-thread system in the I/O. That's important to learn. So that's how Node process is designed. Very similar to the browser, but the browser we see here something called Web API. Also, the Web API is capable to send multi-threads requests over the network as well. But still, a tab would have single thread event loop. And node process has single thread event loop as well. But it has multi-thread system for the I/O. Any questions?
Yeah, Professor, I have a question.
Hmm?
So, as the Node.js will have the non-blocking I/O, and it will communicate with the CPU. So,
Mhm.
what is the processing inside the engine? Just like how the Node.js send the command to the CPU and the CPU process in the non-blocking.
Correct. So let's say you have a script that has synchronous action, read file, 3 synchronous action, 4 synchronous action. The way a script like this runs, we run line number 1. 2, we delegate this to libuv. libuv will utilize one of these threads to read the file content from wherever it is. And now immediately we process line 3 and 4. 3 and 4 are being processed here. Now the file will be read, buffered in memory, and once it's ready, we schedule the callback function in this queue. Now, once we finish all the synchronous code in this script, the callback function is picked up to read really the file content and deal with it inside V8. So V8 is where the real code executes. However, all asynchronous parts are the responsibility of libuv, which utilize multi-threaded system to accomplish the I/O work. When the I/O work is done, it schedules a callback function inside the queue. More requests are coming to be served. We schedule them as callback functions inside the queue. Just acknowledge that, yes, I received your request. I received your request. More and more. This is why Node Web Server is more scalable. Clear?
Yeah. So I have one more question.
Yes.
So example, I have an application that TPS is 1 million requests per second. So when the on request coming, so how I can identify the limitation of the non blocking I/O and the limitation of the pool?
Yeah, the number you gave me, it's dependent on the hardware. So there is not a simple answer here. It depends on your hardware, memory, type of memory, and memory size, and hard drive speed, read and write limit, the network speed, read and write, upload and download speed. So the answer to this is it depends on the hardware. But if we want to compare generally on the same hardware, how things work, we would definitely see that the single thread system is more scalable. Here is a chart. This is number of request concurrency times request per seconds. So we see the blue is Apache and the yellow is Nginx. Nginx is single-threaded web server. Apache is multi-threaded. As more requests are coming to your web server, your performance in Apache is dropping. You cannot, certainly more clients are going to wait. So it's blocking other clients. However, a single-threaded web application was more capable of maintaining higher number of requests over time. So that's just by stat on the same hardware. And I don't think we need to display the second one. This is a memory consumption. More clients you receive on multi-threaded system, every single thread you create, it consumes memory. More requests, you consume more memory, until you reach to a memory limit inside the machine. However, a single thread, because you don't allocate a new thread for every new request, you have a single threaded system. So you see that you have a steady memory consumption for in a single threaded web server. So this is certainly better for scalability as well. Here? Any other questions?
Professor, I have a question.
Yes. Yes.
So as I understand, when we execute, when we call the async line of code, we will dedicate that async code to the libuv. So and then the loop event will pick that operation to be executed in the VA engine. So why do we still need multiple threads inside the libuv? Or in other words, what is the mission of those threads of the libuv?
Which thread?
You mentioned that
has
in the
one thread
libuv.
event loop and multi-thread system for the I/O.
Yes.
And all of these threads, this and this, and this one is synchronous, so one thread as well. All of these live in the same process, which is node process. That's a process. Here you have one thread for V8, and we have here libuv. Libuv has single threaded event loop. This is the maestro. This is the one that's receiving the request or file reads and stuff. And when they're ready, all these functions are pushed to this queue. They're not immediately served, but they are acknowledged immediately. And whenever this V8 is capable of processing more work is delegated through the event loop to V8. Okay, clear?
Yeah, but when will the thread in libuv will be executed? Is it executed in the engine?
Yes, everything is executed here. That's where the JavaScript run in this single thread. Everything runs synchronously.
Okay.
That was probably the first or second question in the quiz today. Everything runs JavaScript synchronously in the V8. You receive a request, the request schedule callback function here. Another request, callback function here. Whenever it's its turn, it will be processed and executed based on your code you assign to the request handler function, basically. Yeah?
Yeah, okay, thank you, Professor.
And here we can identify that, hey, I don't want to block V8. What does block V8 mean? Spend too much time in V8. We don't want to spend too much time in V8. Why? What happens if I spend too much time in V8? The event loop will never be able to pick up anything and process anything. So basically, you block your entire web server. So we need to be careful not to block, not to write anything blocking, which only means that, hey, we need to be careful not to spend too much time in V8. That's the definition of blocking. Questions?
Professor,
Mm-hmm.
it's not like the questions. Previously, you gave an example of the McDonald's, where a multiple thread is just assigned to a single customer.
This is
And that,
McDonald's.
yeah.
McDonald's is libuv. It is the one receiving the request. It has single cashier, and it has 4 chefs. We will discuss them tomorrow to prepare all the food for you. A multi-threaded system.
Yes. So here you are just to emphasize that a single thread is working better. So for my understanding is that Node.js can be work as a good for a API gateway, right?
Yeah, for sure.
But otherwise, I think it performance will not be good as compared to multi-threaded and asynchronous environment, which support multi-thread and asynchronous environment.
To answer your question, it depends. So it depends on the system and what are you trying to accomplish. In 2023, I don't think any company or software is built using a single technology. You will certainly find 10 Node web servers, 10 IIS servers, another 10. So your API is going to be divided on different web servers from different technologies that is performing a certain task.
Yes.
Microservice in your logic, yeah.
No, I'm not going to microservice since you just compare to server Nginx and Apache, and you have shown that how the Apache is lower in the performance compared to Nginx. But nowadays the server architecture has been changed. Even though if I mention about the IAS, in the IAS just actually receive the request, but in the backend, the actual processing can be on different server, like the Kestrel. So that time it will give the better performance compared to Node.js.
I'm not familiar with this type of server, so probably they made some improvements, which is good. Good to understand how this node really works in case you need it to design some sort of software. But yeah, if other I'm not here like saying that other web servers are really like bad. No, I'm not saying that.
No, but
servers,
you just emphasizing that single thread is working better than multi-thread. That has been reflected in the discussion.
For example, Node web server, I just mentioned the last thing is that Node web server, we need to be really careful not to spend too much time in V8. And you will see tomorrow to resolve this, it requires a lot of resources and stuff to solve this problem. So if your code requires a lot of spending too much time processing, so you have CPU bound logic, then probably you should not choose Node.js for that kind of processing. Yeah, I agree with you.
It will good if we use that API gateway. That's it, from my understanding.
I agree with you. Yeah. Any other questions?
So, Bashir, I have question.
Yes.
Yeah. In this image, and sing when they send the code and then send request, and then the OS will execute the task, and after finish seeing the task, they will push the finished task to the queue, right?
Correct. So every time we have an async operation, it's delegated to the async part, which requires always to utilize a thread to be performed by the operating system. When that's done, we schedule a callback function in the queue. Whenever there is availability in V8, it will be picked up to be processed.
It means that when we do another thing, the operating system will do to show up requests in background, right?
The operating system will receive our request and
do it in the background.
Process them, yeah, do it in the background. Also, the operating system has multi-thread system. And once it's ready, it will send you back the data out of this call, and you schedule your callback function in the queue to be processed later in your application. So we will see how this, like, as a JavaScript and C++ code. I'm gonna explain that next.
So mean that in while the operating system process our request, the JavaScript can run another code, right?
Correct. While this is being processed, JavaScript can run other code.
Okay, thank you. Understand.
Welcome.
Professor, I have a question.
Yes.
So in terms of how they work, what my understanding is that the JavaScript running on the browser, that whatever we discussed yesterday, it's almost similar to the JavaScript on the server, like the one that we are studying today. Is there a difference?
The difference would be, here we call it Web API. And literally, the JavaScript in the browser doesn't have I/O. The only thing, you can't read files, the only thing that you can do is to send HTTP request, and it's all immediately delegated to the operating system, which send the HTTP request, and once the response is ready, a request handler function is scheduled inside the queue. Now, the big difference that you will see today and tomorrow as a difference between the client-side browser and Node Web Server is the event loop, how it really works. And that's going to see today after the break. And another difference we will notice tomorrow is how the multi-thread system works, which is also different than the browser because the browser doesn't have I/O. That's something we will cover tomorrow. But as like general concepts, they are pretty similar, where you have single thread V8, single thread event loop, and some sort of you need to acknowledge all the asynchronous work.
Okay, thank you.
You're welcome. Any other questions? Yes.
So as I understand is when we have a request from V8 to execute a task, so then it will delegate to libuv to send a request to the event loop. So my question is, if the queue is full, so do we have another component to handle it, or the item will be lost?
If your stack queue is full?
Yes, so let's say in the step 1, send request to UF, right? And it will be send a request to the event loop, send the event to event loop, right? So it will be located on the queue.
Let's say this operation was set timeout. When set timeout is seen here, it's immediately delegated to libuv. Libuv, based on the time you specify here, it's going to push this function to the queue. But the stack is immediately jump to the next line of code. So I'm not sure what do you mean the stack is full.
Yeah, so my question is, do we have any situation which the queue will be full and we cannot send the event to the queue?
If you have, for example, a for loop that's calling functions in a recursive way, you will make the stack completely full, and you immediately see an error that the maximum call stack is full. You cannot exceed calling too many functions within the same.
So it means if the queue is full, then we can receive immediately the error. So we don't.
Once the stack is full, you completely fail. The application fail.
Yeah, thanks, Professor.
And whenever one line is taking too much time also is a problem. Why? Because you're blocking the event loop. So that's another issue.
Yeah.
We should be careful not to have these two issues. Any other question?
Professor, I have another clarification question actually, not related to this. So since B8 actually executing the JavaScript code, so the OS actually is not just processing the JavaScript code. So when it converting to, from my understanding that it converts to the machine level code. So when it converts, so it also there is some cost, right?
I didn't understand the question.
My question is that the B8 engine actually executing the JavaScript code, right?
Correct.
So our OS actually does not understand the JavaScript code. It needs the machine code. So as it looks like the interpreter here.
Yes. Yes.
So it will take much more time to convert the every single statement or every single line of code to the machine code. So compared to other language, they just created the machine code when they build the project and they build the application. So it does not require any runtime conversion time. So it is the another time and the bottleneck of the B8 engine.
What you're missing here is how the V8 engine works. So the V8 engine works is an interpreter plus compiler too. Something that we will discuss in the third week, I believe, first day, to tell you how TypeScript is superior to JavaScript and why typing all your code can make your code run really fast. So there are other things in the background that we need to understand before we realize that why this guy is really fast.
My question is that actually B8 engine needs to be convert the JavaScript code into machine code, right? Line by line interpreter.
Yeah.
So other language like Java, when we build a project, it creates a bytecode, and when we execute it, and then it immediately converts it to the machine code. So it does not require to convert it machine code when it process. But here in VS Code, it requires to convert the every single line of JavaScript code into machine code when it is processing. So it's my question that it's also here takes sometimes when it's processing. So it should be and the slower.
I agree with you. Yes, but that's the only way that we could run web applications. But I do agree that interpreting the language at runtime, it is slower than running the application immediately with the compiled code.
Okay.
But the only thing I wanted to explain further is that you will see later that once your interpreted code is compiled, now your code will really run fast at some point in the future. We will see that later. So there is a profiler here that once certain logic execute more and more, this compiler is going to optimize that code so it runs just as similar as a compiled language. So there is features within the JavaScript engine that takes advantage of that. But we will discuss that details later. Yeah, but I do agree with you that interpreting take time.
Okay.
You're welcome. Any other questions? Let's take a break, and after the break, we will take a look at the event loop. Right, welcome back everyone. Before we continue looking at Node.js, let's answer a few questions. I have here a piece of code, and there's a question whether this piece of code is blocking or non-blocking. Remember, blocking only means spending too much time in V8. For a piece of code like this, it's certainly blocking, even though I have an asynchronous operation. And basically, this is the line that is blocking. This line is going to wait forever. And you will never process the last line. Why? You have 1, 2, 3, 4 lines of code need to be processed.
Because the set timeout function will execute when the B8 engine call stack is empty. So since set timeout will go to the queue, and in the meantime, while is processing infinitely.
Yes, so I'm going to explain that. So the first line is going to set open to false. That's the first line. Second line is going to schedule this function with f to be pushed into the stack to be pushed into the queue after 1 second. Now we're done. Number 3, we're checking on open. And open is false, not false is true. So we keep looping in here. We are waiting for open to become true, which is going to happen inside this function. Now, after 1 second, the function will be pushed to the queue. However, the event loop will never be able to push the function to V8. Why? V8 is still busy at line number 3, checking on open. The only time this function will be picked up to change open to true is when we finish line number 4, which never going to happen because we will keep checking on open forever and the function will still waiting here inside the queue forever. So this is certainly a blocking code because we're not only spending too much time in V8, here we're spending infinity in V8. So this is certainly a blocking code. Let's see another example. Here I have a function that is going to that has for loop. This is 1 billion 9 zeros. And I'm calling this function in my application 3 times or even 1 time. And the question is this code blocking or non-blocking? And the answer is it's a blocking. Why? This code spends too much time in V8. How? Function declaration. 1, easy. 2, when 2 is called, this for loop is going to consume a lot of CPU power, blocking line number 3. Only until it finishes, we start processing line number 3, which in its own turn, it's also going to run this for loop. This for loop is the one that's going to spend too much time in V8. Hence, I have code that spend too much time in V8 it is blocking, regardless of how many times I call it. Clear? Now, in the next slide, I took this line of code and converted this line of code to become asynchronous. How? I just put it inside a set timeout. And I delayed the processing to become after 5 seconds. And the question is, this block of code is blocking or non-blocking?
Non-blocking.
Why?
Because every time when we call the add function, it will go to the set timeout function will actually go to the queue, and then it will return.
Does this code is going to spend too much time in V8?
No.
Yes.
Uh,
First, start. Second,
yes.
you schedule this function to be pushed after 5 seconds, right? So we have function after 5 seconds. Next. So all you did when you made the code async is that you're going to deal with the blocking code later. Then be immediately F5000. Then the next line F5000. Then you print end. So you print start and end immediately. But what happens when all of these functions are pushed into the queue? Now, when the first function is picked up to be processed in V8, it's going to spend too much time.
Yes.
Then when the next function is picked up, it's going to spend too much time. So this is very important things to notice here, that making something asynchronous doesn't make it non-blocking.
Yeah.
So this is what we learn in this slide. Making an operation async doesn't make it non-blocking. Because blocking simply means spending too much time in V8. And if you have a script that runs now or later, and it's going to consume too much time in V8, it is blocking, regardless if it's run now or later. Async just means it's going to be processed later. Any questions?
Yeah. Thank you, Professor. Yeah. Got it.
Now, most of you are going to start downloading Node.js. And I have some recommendation for you that when you go to Node.js, all of you, if you have Node.js or you don't, go to the Node.js website, make sure you have 18.15.0. Do not download the current version, 19.8.1, because that is going to create a conflict with the Angular CLI later. So if you have this one, and install it and run a recommended long-term support version, the latest one, which is 18.15.0. That's the version that we're going to work with. Now, when you do that, let's understand basically what is Node. And so V8 is basically a project that's made by Google. Is the source code, and it is an open source JavaScript engine. And this engine is written in C++. If you check the source code, it's 100% C++. Small part is just JavaScript that's going to read the JavaScript as an input. and parse it. That's the JavaScript part. And it says that this V8 can run as a standalone. So you can just download this code, build, and run it. Or it can be embedded in other type of C++ applications. And that's where Node take advantage of this and included the V8 JavaScript engine as part of the Node project. So if we inspect the Node.js source code, we see it's a code, we see that it's a project that has 50% of the code is JavaScript and another 50% is C++. So how Node works is that as a developer, you send JavaScript code. This JavaScript code has hooks with the C++ part, which is going to accomplish whatever result that you need to do, reading from a database, or probably reading from the hard drive, or making a network call, and then send the result back to the JavaScript part, which you receive as a developer. So as a developer, you work with 100% JavaScript experience, but behind the scene, there is 50% that's C++ code that's doing the actual work. And if you want to inspect the source code, we will see inside lib, we will see all the JavaScript files that you are going to include. These are Node core modules like HTTP and path and OS and URL, V8. All of these are the Node JavaScript core modules. Now, all of these modules, they have hooks with C++ side. Where are these C++ code? We see it in a folder called source. If we inspect source, you see that most of the libraries that are written inside source are C++ code. That's the code that's doing the actual job. We also notice a folder in this project called dependencies. So also Node project depend on third-party libraries like broadly compression and decompression project, base64, which is going to encrypt data. There is an HTTP libraries. There is npm, which is Node package manager, which is something we're gonna talk about tomorrow. And we have here our famous libuv. So this is basically libuv, which is a project that Node implemented to have its asynchronous functionality. And we see that another dependency that's very important, which is V8, and that's what we displayed in the chart earlier. Inside Node, we see V8 and we see libuv. And these are third-party dependencies that's borrowed to build Node environment. So earlier, I explained to you that how everything works in here, but we did not talk in details about the event loop. Today, we're going to see how this event loop works in details, and tomorrow we'll understand the thread system, how it works. So what about this event loop? Well, actually what you see here is one queue, and the Node event loop is not one queue. It has 5 queues. So let's see how basically all of these work and how we deal with them.
Professor, can I ask you questions? It's simple.
Yes. Yes.
How actually the JavaScript code converted to, let's see, I mean, how the B8 engine actually converting in JavaScript code since it has been written in C++. So I'm confused how
The JavaScript engine doesn't translate to C++. It translates to machine code.
how C++
V8,
code actually understand and the JavaScript code is.
check the source code. Check the source code simply.
Just you have time. I'm just
Yeah.
curious.
Yeah. Node.js, GitHub. If you're curious, just satisfy your curiosity by checking the lib folder. Pick any dependency, say HTTP, and see the source code that's creating the hooks with the C++ side. All these properties, I assume, all of them are the C++ side. And see all this requires. These are requires for the hooks, basically. So let's get one of these hooks. Let's say HTTP common. Here we're creating HTTP parser and symbols. You see this internal binding. This internal binding is the method that's actually bind JavaScript function call to C++ function call. So it is the one that's literally calling the C++ function when you call it. This is internal binding. So dig inside this guy to see all the how it works.
Thank you, Professor.
Welcome. So the event loop. We have 5 queues and not one. The first one is called timers. Every single time you call set timeout or set interval and you pass a function with time, these functions are pushed in the timers queue. The next queue is ticket. Okay, so the first timer, the first queue is the timers queue. We discussed that every time you pass a function to set timeout or set interval, the function is queued inside the first queue. Second queue that we see in node event loop is called pending callbacks. We don't really care too much about this queue because operations that, for example, when you close a HTTP TCP request, you need to clean up some variables and stuff. All of these callbacks internally are scheduled here in the pending queue, and it will clean up some work for node internal work. So as developers, we don't really schedule anything in this queue. The third queue that we see here is called idle. And idle is also a queue that whenever the event loop is waiting for any asynchronous job, let's say you have set timeout that's happening after 10 seconds. The event loop is literally empty, but it needs to wait somehow. It doesn't keep looping. It needs to wait in stage until a new asynchronous work is assigned. And that's what the idle stage is for. It's just to wait until more asynchronous job is scheduled inside the loop. The fourth queue is called the pull queue. And this is the most important queue that we deal with. Why? Because every single time you try to read something from the file system, every single time you do encryption or decryption, every single time you do compression, every single time you receive a request or you want to send a response, all of this work require callback functions. And all of these callback functions are going to be scheduled inside the pull queue. Next queue, we have something called the check queue. And we have an API called set immediate. We pass a function. When we call set immediate and we pass a function, this function is scheduled here. The difference between set timeout and set immediate, set immediate is just like set timeout with time 0. However, set timeout 0 is going to immediately push the function here, while set immediate doesn't accept any time. It's going to push the function here. So set immediate is similar to set timeout 0. However, each one of these API will schedule the function in different queue. Now you would probably wonder, why would I use set immediate instead of set timeout 0? Why would I want to schedule something here instead of here? Well, actually, there is another queue here called close queue. So every single time you listen on close event and you schedule a function, this function is pushed here. So sometimes, for example, you are processing something from the pull queue. And if you need to immediately have some sort of cleanup, you can schedule it in the check phase rather than waiting for the close callback functions to finish before you loop back into the timer queue. Because the way the event loop works is it starts from the top. And we have some sort of a limit. Let's say the limit is set to 5. In actual real life, it's not 5. It's a different number. Just for example purposes to understand how it works, let's assume the limit is 5. So it starts with the timer's queue and it processes functions until it's completely empty or until it reaches the limit. So we reach to the limit and then we pause and we continue to the next queue. We process until hard limit and then we continue. This is idle. If there is nothing else, we're going to pause until something else is scheduled to resume. Next, now when we process the pull queue, we have calculated limits. Every single time we come to the pull stage, we calculate a different limit. Why? Because there are so much work need to be processed from the pull queue. So we don't rely on a hard limit like all the other queues. All of the other queues, they respect a hard limit set, except for the poll queue. Whenever we reach to the poll queue, we calculate a calculated limit to say, oh, this time I'm going to process 50 functions. The next time, maybe we have less work, maybe 3 functions. So we calculate a limit, we process everything from this limit before we move to the next queue, hard limit, or until it's empty, and then we move. And once we finish the close queue, we go back to the top, and we call this entire cycle one tick. So a single event loop tick is going over all of the queues, finish all of the queues to the hard limit or the calculated limit and the calculated limit in here, and going back on top again to continue further processing to the event loop. And when I mean processing, I mean take this function, push it to V8. When V8 finishes, I'm going to push the next function V8. Until I reach the hard limit, I push this function to V8, and so on. So that's how the event loop in Node works. So what we used to see as something called macro task queue, now in Node, we see that it is not single queue, but actually 1, 2, 3, 4, 5, 6 queues that are going to be processed before we finish the single tick. Any questions?
Professor. So my understanding is set immediate will print out first before the set timeout of 0 millisecond.
No. Our understanding is that immediate schedules a function in the check queue. No one guarantee when this is going to be called. So maybe what if you are already in the close and you schedule something in the check? Then you have to go over all the queues before you reach to the check again. So it depends where the cycle of the event loop is paused or processing at. So set immediate, schedule something here. It does not mean that whatever is here is going to be processed before anything else. Okay? Any other question? Sure, you're welcome. Any other question?
Hi, Professor.
Hi.
So what is the best practice when we should use set immediately and when we should use a timer? Which one is better?
Let's delay this question until I explain the other queues. We have more queues going. Let's understand all the queues before we can answer this question. Just give me 5 minutes.
Okay.
Any other question about this event loop? Now to complete the picture, so we have timers, others that we don't care about, poll, check, and close. This is event loop. Good. It is our queue. Now we have V8. We already know that with V8 comes microtask queue, right? And there is an API to schedule a function in this microtask queue immediately. It also exists in the browser, by the way. It's called queue microtask. If you call queue microtask and you pass a function, the function is pushed here. So it immediately becomes asynchronous. You don't need to return from a promise, and you add then to schedule a function here. You can make something to be pushed in the microtask queue by calling this method, which is a global method, and pass the function to it. It immediately becomes asynchronous and it's pushed here. So now, as you probably have guessed, microtask queue does not have limits, and it needs to be completely processed before the event loop is able to pick anything from the regular event loop, similar to the browser. These queues have hard limits, calculated limits. The check phase has hard limit. So we keep cycling over here. This guy does not have limit. So if you pushed like 1 million functions, that's going to block the event loop because this queue has priority over the event loop. The event loop can't function until V8 finishes its current work plus all the microtask queue functions. So you have to be careful. And inside libuv, there is another queue. And this queue is called next tick queue. So if we take a look at the global objects that exist in node environments, we don't have window and document and all that stuff. Instead, we have console. We still have something called global. We have also process. Process, it's a global object you can access. You have all the set intervals and immediate and timeout and clear, all as globals. We have something called directory name, file name, exports, module, and require. We will talk about them a little bit tomorrow. We see how Node customize this, but we have something called process. This is part of the global objects that you can immediately use in your script. So now, how do we schedule anything inside NextTick? Process global object has a method called NextTick. And this guy you can pass function to it. This function is pushed here. Now, how does this play any role between everything else? Well, this guy has the first priority, this guy has second priority, and this guy has the third priority. Simply put. So at any time, let's say you are in the event loop, and once you finish your function, if there is anything in here, it will be processed before even the microtask. This next tick queue has nothing to do with the event loop. Now, and I understand that the event loop, looping over everything, all the queues, we call it one tick. But this next tick queue has nothing, absolutely nothing to do with this tick. It's a horrible name. Whoever named this queue next tick is, I don't want to call names now. It's an awful person. They shouldn't name it next tick because a tick, as we know, it has nothing to do with this queue. I would rather call it priority queue, for example, because at any time we finish from function and we want to, before we move to another function, everything in the next tick need to be processed. That's number one. Even though if I have microtask queue, this is the first queue that need to be completely processed in V8 before we move to the microtask queue, completely processed. And the last one, once these both queues are empty, that's when the event loop can proceed and continue its tick. So that's basically all the queues that we use when we build software in Node.js. Now back to our friend's question. Which queue should I use? Yeah, it's always, the answer is it depends. If you're here and you need something to be cleaned up immediately, next tick is your first choice. If something like less important, you can schedule it in the microtask. Now, scheduling within the event loop, it's always no guarantee which one comes first. And unless you know that I am in IO stage, if you know if you are in the IO stage, then you can guarantee that the next function is going to be check. Unless there are other functions in the poll stage, then you will pause, you process next tick before you continue to the next poll. So the answer is always, it depends what kind of work you need to finish and when. But know that if you are in the poll stage, after finishing the poll queue, the check queue will always come next. But if you have some sort of code that generally running from the global scope, even in the node documentation, they tell you no guarantee that the timers will come before check or check before timers. Unless you really inside the stage and you know that I am inside the stage. Any questions? Now that we understand the event loop, let's try to reason about some sort of coding example, this one, and try to figure out what is the output of this code. And I have here 6 lines of code, each one of them, 1, 2, 3, 4, 5 lines of code. Each one of these lines of code is asynchronous. So all of them are delegated in V8 from V8. So here we have V8. Here I have the micro. Here I have libuv. Here I have timers, poll, and check, and others. I'm not going to display all the others, okay? This is the event loop. And we have also another queue, which is next tick. Now, this 5 lines of code needs to execute. As you can see, all of them will delegate job to libuv. The first one, libuv, it's going to process this promise immediately because you are calling the function. And then it's going to schedule function 1 in the microtask queue. It's a promise. I'm going to call this function 2, function 3, F4, and F5. These functions, callback function, will be scheduled somewhere. The first one inside then is going to be scheduled inside the micro. It comes out of promise. Second line, libuv, it's going to immediately push F2 into the timers. Nothing will be picked up before we finish all 5 lines of code. Line number 3 is going to push, it's going to be delegated to libuv, which in turn pushes F3 inside check stage. Next line, queue microtask, delegated to libuv, which is going to push F4 to the microtask queue immediately. Line number 5, we push F5 to the next tick queue. Now that I finished everything in V8, finished all my code, now the event loop will start triggering, and I have a lot of asynchronous work. The first function to be picked up is F5. Why? Because this one has the first priority. Remember the priority. This is 1, this is 2, and this is 3. So the first one to run is F5. Second would be F1 and F4. We need to completely drain the microtask queue after we drain the next tick queue. After we drain the microtask queue, now the event loop is going to trigger and we will run F2 and F3. Since both of them are coming from a global scope, let's say, most of the times you will see F2 and F3, but sometimes you will see F3 before F2. And that would be the order where all these functions are going to be executed. The guaranteed ones is F5 and anything else in here, F1 and F4 in order, and then the rest if there was any rest in here, and the event loop functions that are pushed. Most of the times you will see F2 and F3, but there is no guarantee. Sometimes you might run the code and you will see F3 and F2. It might happen. Any questions?
So, Professor,
Yes.
so I have a question that in the last slide, if you give us a question in exam, we can write F2, F3, or the F3, F2. It's okay, right?
Didn't quite get the question. Can you please rephrase?
It means that if you give question, write the order of the output.
Yes.
So in the last slide, we can write choose two of them to write down, right?
Yeah.
So,
Yes.
why we cannot guarantee the order of the F2 and F3?
Oh, that's what the documentation says.
Ah,
That's what the documentation says. Yeah.
thank you.
Pull up the documentation. Node.js event loop. Oh, that's not the event loop. Yeah, so what is the event loop? And you see the queues and stuff. And as you're reading each stage, what does it do? See here? It says the order in which the two timers are executed in this example is non-deterministic, as it is bound to the performance of the process. So we schedule timeout and immediate. And when they run the code, sometimes timeout comes before immediate and sometimes immediate before that timeout. However, also in the documentation, you read that if they were coming out of IO cycle, so they are coming from the poll stage, here you're saying, I'm reading a file. So this function comes after you read a file. So after you read the file, it means you are currently in the poll stage. And when you go out of the poll stage, you guarantee that immediate comes before the timeout. So in this example, you always see immediate before timeout. Yeah, so that's just how the documentation explains the event loop.
So
Any
excuse me, I just had a connection issue.
Yes.
And as you mentioned earlier, the macro task wait immediately becomes synchronized. that's what you mentioned, right, earlier? Micro
Say it
task
again.
immediately. So micro
Say it again.
task immediately becomes synchronized.
No, microtask is immediately pushed to the microtask queue. It doesn't make it synchronous. It immediately makes it asynchronous. If I mentioned synchronous, then it was a mistake. Yeah. When we call, when we call queue microtask, immediately the function become asynchronous because it is pushed to the microtask queue immediately. And in this slide, you will see all the ways that you can make an operation asynchronous in Node.js.
Okay. So the promise is synchronized, right?
The promise
but
is,
it has asynchronous value, but it's synchronized.
Yeah, when you create the promise object, it's synchronous. Only your returned value, the resolve, is asynchronous.
Okay.
And if you'd like to write down here the queues, set immediate is check, set timeout is timers, set interval is timers, promise is microtask, event emitter would be the poll, async await certainly microtask because it comes to await a promise. Next tick is the next tick queue. And this one also micro task queue. So that's how we make all things asynchronous in Node.js.
Okay. Another question is the set timeout is so for example, when we do set timeout 5,000, right? So it's equal to 5 seconds. So when we run the code, does it for example, if you do some console, whatever, and then it show up as after 5 seconds, or does it happen after all the synchronous codes executed? Then it will happen.
Correct. After the all synchronous is finished. So when you say set time out and you express a time, you say this is the time when the function is pushed to the queue. This time doesn't mean this is the time of execution. This is the time of pushing the function to the queue. You don't know when the function is picked up. Maybe there's other 100 functions waiting before. Yeah.
Okay, thank you.
Same for interval. The time in both only means that this is when we push the function to the queue. This is not execution time. That's it for today. Today, I want you guys to understand the event loop in details, how it works. And I want you to understand this, that making something asynchronous doesn't mean it's non-blocking. So I wanted to understand what is the meaning of blocking code. And to explain, blocking means spend too much time in V8. Tomorrow we see if we have a blocking operation, how we deal with it. We will learn a few techniques. Today we need to identify it, understand it, and understand that asynchronous doesn't mean non-blocking. And understand how the event loop literally works in Node.js, these queues, and that's basically understanding Node internals. Any questions?
Professor.
Yes.
I have a question. So blocking is mean that we spend too much time in the VA. So any what definition of the spend too much time is either
it's relevant. It's relevant, yes. So you have here queues. We have also another queue. Doesn't matter. That's what we learned today. What is blocking? It's just spending too much time here. And how much is that time? It's relevant. Some applications, it's okay to spend 1 second. Some applications, they don't. It depends on the number of users. It depends on hardware. So you have to benchmark to set your own too much, basically.
Oh, okay, thank you, sir.
Welcome. But definitely it's like kind of logic. Let's say you have an application in Node and you're receiving a JSON array that contains 1,000 objects, and you need to map over all 1,000 objects before you send a response. For loop for over 1,000 objects, mapping them, that's too much, I would say. So sometimes it's just like, oh, that's definitely something I don't want to do in V8. We will do it differently tomorrow. For the homework today, it's
Professor,
not quite.
I have a question.
Yes, yes.
So before putting the function into timer, where the set timeout or set interval function is being stored.
Okay, what's the question?
My question is that before putting into queue, and then the timer, like set timeout, set interval function, where this function is being stored?
In the libuv API, just like the browser yesterday. So whenever you call set timeout, libuv handle this. When the function is due to be scheduled, it's gonna schedule it in the queue. But yeah, that's the job of libuv. When you say read file, there's no queue involved, right? When you read the file, libuv immediately it's gonna start reading the file. When the file is read, we schedule something in the. So that's the job of libuv basically.
So it will check whether the given time has been spent from the elapsed or not.
Correct. It will keep track of the time, and whenever the time is due, it's going to push the function to the appropriate queue.
So how it manages those code? I mean those events like set timeout, set interval. There are a lot of set time functions being called. So where it
By
is stored?
order, first come, first served. So if you have a lot that have the same time, first come, first served, they will be pushed by order.
Okay.
libuv is an open source as well project. Feel free to read its source code. It's really fun to dive into this project. Read the source code of the event loop inside libuv. You will literally see it's a while loop that's checking on so many things before it start pushing stuff to the queue. I mean, at some time I did read stuff like that, and it's really fun. So don't be afraid of exploring more. Any other questions? The homework is pretty simple.